All right, good morning everyone. My name is Peter Goodspeed. I'm a master's student at University of Michigan School of Natural Resources and the Environment. And my mentors for this project are Ashley Elgin and Mark Rowe. And this project entails the geostatistical modeling, the spatial distribution of dreissenid mussel biomass throughout the southern basin of Lake Michigan. So as many of you know, probably know, dreissenid mussels are invasive species. They were introduced in the Great Lakes in the late 1980s, and the zebra mussels came first and proliferated throughout the nearshore area in the lakes, and were quickly displaced by the quagga mussels, which are better adapted to the colder, deeper environments. And in Lake Michigan specifically, we see the progression advance from north to south. So here at GLERL, we have a long-term benthic monitoring program that includes sampling from 160 sites throughout the entire Lake Michigan every 5 years. And we also have 42, or included in that are 42 sites in the southern basin, which are sampled annually. These samples are collected using a Ponar grabber, and then the samples are processed for all the benthic organisms, but I'm just going to be focusing today on mussels. And so we essentially count the number of mussels in each sample to determine their density, and then that's converted to biomass using length-mass relationships and length-frequency distributions. And biomass is important because we can use this as an indicator for filter feeding capacity of these organisms. So what exactly do we do with all this data then? Well, one of my advisors, Mark Rowe, and a few of his colleagues here at GLERL had a paper published in Freshwater Bio last year that looked at the spatial distribution of mussels and their filter feeding effect on the winter-spring phytoplankton bloom in Lake Michigan. What was really cool about this paper is it included a geostatistical model that predicted mussel biomass at unknown locations, and it was able to quantify uncertainty in those predictions. And this method of spatial interpolation is called universal kriging. So what kriging does is it utilizes a combination of spatial autocorrelation, the idea that closer things are more related, and then adds additional predictor variables to predict mussel biomass at unknown locations. And here on this slide we can see a figure from that paper I just mentioned that maps the spatial distribution of mussels every 5 years, and then the covariates that are used for predicting the mussel biomass at unknown locations. And these covariates include depth and spatial coordinates. So I was given data that was annual data from the southern basin to incorporate into this model. And then I wanted to explore the addition of or substitution of new variables that could conceivably lead to model improvements. So I looked at substrate, total organic carbon, and hydrodynamics. So here's one of the southern basin, a couple of the southern basin maps that I generated here. And if we can see, the units right here are dreissenid biomass in grams ash-free dry weight per meter squared. And to get a good idea of how well the model fits the data is essentially, if you look at the color of the dots, these represent the sampled mussel biomass. And it's the model is a good fit to the data if the color of the dots is the same as the color in of the surrounding area. So zooming out here, we can see the spatial distribution of mussel biomass between years 98 and 2014, and for every year except for 2009, which there wasn't a survey conducted that year. And these are some really cool maps because we can see that this peak right here, which was from the zebra mussels, and then those kind of disappear, and then the quaggas come in, and we see a peak of quaggas here in 2010 in this depth range between about 30 and 50 meters. And then after that, they kind of start to spread out here and invade some of the more deeper regions of the southern basin. So how exactly are we going to go about improving this model? So I initially looked at substrate and total organic carbon using these variables to predict mussel biomass at unknown locations. And there were some limitations to this analysis. The data that I had at each of the stations was very qualitative for the sediment grain size. And also I was limited in my ability to create a substrate grid that represented mean grain size throughout Lake Michigan. And I did some regression trees, and they proved to be unfruitful in this analysis. So that left me with looking at hydrodynamic variables. So Ackerman did a study in '99 that it was a controlled study where he basically took a flow chamber and he put dreissenid mussels in the flow chamber. He discovered that if he increased the velocity of the water to 10 centimeters per second, it led to a doubling of the clearance rate of the phytoplankton. And then after the velocity of the water exceeded 20 centimeters per second, the mussels began to retract their siphons back into their shell, and it led to a decrease in the clearance rate. So this paper gave us a nice optimal range of the velocity of water at which mussels like to feed. So how could we incorporate this information into this model? Well, we essentially needed to figure out the frequency of optimal bottom current in Lake Michigan within that range between 10 and 20 centimeters per second. So in order to do this, I got internal circulation data from the Great Lakes Coastal Forecasting System that included eastward and northward water velocity at the bottom boundary layer. And I also got wave data from the same model that included wave height, period, direction, and depth. And you may be wondering, what do waves have to do with circulation at the bottom of the lake? Well, when a wave goes over a certain point, it generates an orbital velocity that exponentially decays with depth. So you see here, you can actually use wavelength and period in addition to depth to calculate orbital velocity at different locations. And orbital velocity, it's not just positive, it oscillates back and forth. So it was necessary to use vector addition to combine the orbital velocities with the internal circulation data. So this map here on the left is the optimal current frequency using internal circulation data alone. The middle map is optimal current frequency for orbital velocity. And then after I added the two vectors together at each node, I came up with the map on the right, which combines the two. And this data was 3 hour data for years 2010 through 2015. So looking at the map here on the right, essentially reading that those really dark crimson areas are essentially areas where the velocity of water falls within that range between 10 and 20 centimeters per second, 26% of the time, which is pretty cool. And then kind of zooming in on the southern basin and looking at bathymetry, we see areas where current frequency departs from bathymetry, and then we also notice a relationship between current frequency and slope. So I essentially took current frequency data at nodes nearest to the stations, and I did a regression tree analysis to see how good of a predictor this new variable is for the biomass of mussels. And I looked at pairs of years, and to avoid overfitting on these regression trees, I pruned them using the lowest cross-validation error. So where you see PFT, that stands for prune from tree. And then looking at the adjusted R-square values over time, we see how goodness of fit changes over time with the different variables in the regression trees. So I essentially replaced the depth variable with current frequency in the current geostatistical model that we have. And we can see some similarities that these maps have with depth, but there are a lot of differences where we see areas that are more clustered instead of seeing like a ring that goes all the way around. But zooming in on 1 year, comparing 1 year with depth and current frequency, we can see here there are some areas where maybe we wouldn't expect to see as high of a mussel biomass at the deeper depth here. But with the current frequency variable, we get a better fit to the data, which is really interesting. So some next steps in kind of refining this model, I'm currently working with the script to include both the variables at the same time. And that'll be interesting because the way the model works is it utilizes leave one out cross-validation, so it'll add or drop variables depending on what fits the data better. And my hypothesis is that in the earlier stages of mussel progression, we'll see depth as a better predictor for mussel biomass. However, after the mussels exceed their carrying capacity and food becomes more of a limiting factor, we'll see current frequency as a better predictor variable. And then once I'm done refining this model, I'll perform conditional simulations that will determine total biomass within current frequency intervals within depth intervals. So that'll be pretty cool. Some neat applications of this new hydrodynamic model output is to determine the best place to establish new stations in the southern basin. So Ashley came to me and she was interested in putting a couple new stations here on the C transect and then one new station on this B transect here. So using the model output data, I looked at the characteristics of depth and current frequency between these two stations. And here, for example, she decided to put B8 right here where it has a similar current frequency to B4. However, it's much shallower than B4. So that'll allow us to tease away that relationship between mussel biomass and depth and mussel biomass and current frequency. And then here we can see the C stations she added. And once again, here, for example, this C10 has a similar depth as C6 here. However, the current frequency is, optimal current frequency is much less. And then this is just, these are the locations of the new stations within these transects here. So some implications of these findings, if we really are onto something here and adding this hydrodynamic variable to the model, if this does lead to model improvements, this will be great. You know, we'll be able to better predict mussel biomass at unknown locations. Furthermore, we'll be able to apply this model to predicting the distribution of biomass of other suspension-feeding benthic organisms. If the optimal, if their optimal feeding water velocity is known, and I think a really cool application of this could be forecasting the distribution of new invasive species, including the golden mussel. However, once again, we'd have to know the optimal current at which golden mussels feed before we could incorporate that data into the model. So I'd like to thank Mark and Ashley for all of your guidance and support and patience with this project. I certainly learned a lot this summer. This was pretty cool. And yeah, I'd like to thank the rest of the Summer Fellows. You guys are awesome. Any questions?
Any time for questions? So in the first slide, first several slides, you mentioned there is a comparison between like over the years, and you said that there is one peak of the quagga mussel and several peaks of the zebra mussels. How can you tell?
So when I did this analysis, I did it for biomass of both mussels. However, we just know that in '99 the zebras came in first, and then were soon replaced by the quaggas. Right, correct. But this is these data are a combination of the two, so total biomass of all the dreissenid mussels.
Can you explain, maybe you did, I just missed it, can you explain what's going on at the bottom of all the years, what are those indicating?
So these are the different covariates used for the prediction. So here, for example, we just have depth as a predictor variable, whereas here we have depth and then the y-coordinate and the y-coordinate squared. So we also have linear and quadratic spatial trends.
So certain years, so like 2008, that was the best predictor by itself, or is that just all that confused?
Yeah, both. So whatever model fits the data the best. And that's why once we get depth and current frequency, it'll be interesting because we'll see where it adds depth or current frequency or where it drops either of those.
Come on.
Mm-hmm.
So I can see where the current frequency would really make a difference in biomass because you've got enhanced feeding rates.
Mm-hmm.
Did you do anything to look at potential recruitment or of new areas, so dispersion or spread into new areas?
I didn't really look at that, no, but that would be something interesting to look at, to see maybe areas where there's that optimal bottom current that don't currently have mussels, and then see kind of rate of growth in the area. Yeah. Interesting.
Any questions for Peter? All right, thank you very much.
Thank you.